So in the previous video, we were looking at the permanent impact model, and we saw that we want to minimize the expected cost of our execution, and what we choose really is the sequence of delta VTs, or the child order as they are called in the market, to minimize this impact. Note that we minimize on expectation. That means that, think of it as you're executing orders, say on behalf of a client, over and over again for this asset, say every day, every minute, and then you average them out. So when you average them out, the Brownian component should be averaged to zero, because we are in a drift in this case, and what we are left is the impact of our decision on the asset. So the final cost we end up paying really depends heavily on our decision process on average, and imagine we're averaging a lot of cases here, so a lot of execution, so we don't have to care about the variance for a second, yeah, so it's like we are inserting a drift against us, because if we are buying, say, this pushes the price up, so against us, because we need to buy at increasingly higher prices. So I was saying we want to minimize this sort of drift impact that we insert in the underlying process in the context of permanent execution. So let's see how we go about doing it. We can solve it recursively. That's the typical dynamic programming approach. And the idea is quite simple. You imagine that you're sitting time t, and then you want to just find the optimal solution for one time step, so delta t in this case, delta vt, and then you assume that you'll continue optimally. The way to solve this is actually backwards. You start from the end, you sit at time capital T minus 1. In that case, we'll see it's very simple what you need to do, and then you walk backwards. That's a typical dynamic programming approach. So more formally, we want to solve this called Bellman equation, which says that if you are at time t, you make this decision, you observe what the price is going to be at time t minus 1, and then you continue optimally. So we are trying to find just one step. In this case, sorry, it should be delta vt here. So you find the optimal thing to do for one time step, and then you continue optimally, which means that you're going to find the next optimal thing one step, but they're not optimal action for one step at t plus 1, and so on and so forth. As I was mentioning, the way to solve this equation is going backwards. So we start at time capital T minus 1, so we have only one period to go. In this case, the solution is quite trivial, because we have this constraint that we need to finish by time t. So at time capital T minus 1, so we need to finish at time capital T. So at time capital T minus 1, this is the amount we had to execute. So imagine we started at x0 equal 100. Now at T minus 1, we are at 10. So capital T minus 1, we have 10 units to execute. We don't have a choice. We need to finish by this interval, and since the last execution available is at time T minus 1, the amount we execute is just equal to whatever is left there to execute. So that's trivial. But this allows us to compute this component here at time capital T minus 1. You'll see that once we plug things in, all that the dependency is really on the price at st minus 1, and sort of the quantity to execute xt minus 1. So here I'll denote by E t minus 1 the expectation conditional. So there's a conditional expectation, conditional on the information we have at time t minus 1. This is also in more technical terms called the filtration up to time t minus 1. But here all we really need to know is what was the price. So we assume that we are sitting at time t minus 1, so we went back in the future, so forward in the future, and we know what the price is at t minus 1, and we also know, of course, the amount to execute time t minus 1. So that's what our filtration includes. How do we go about? So this is the cost of the last execution, the amount we will execute, and this is the price we'll pay. So what we do is we go and substitute the expression for ST into here. So this is what we saw earlier in case of permanent impact. So it was the price at the previous time plus the amount we moved the market against us, plus some sort of random noise, and this gets multiplied by the quantity we execute. So this thing into square brackets is actually a price, and this is a quantity. One thing you can think of is this quantity, when multiplies by theta, which is our market impact coefficient, gets translated into a price. So this product here is the price we pay due to our child order execution here. Yeah, when you expand and solve this question, the Brownian motion goes away because the expectation of the Brownian motion at time t minus 1 is equal to 0. Again, if you don't know what the Brownian motion is, don't worry, think about it as this is a random variable with 0 mean in expectation. So this disappears, so you're left with this term, and multiply by this term. You go back and substitute the optimal thing to do at time t minus 1, which in this case, it just execute whatever you need to do. There's nothing optimal, if you want, about this. It's just we didn't have to optimize. We just had the constraint which told us what we had to do, and this is the cost that the expected cost, okay, that you're going to be paying at time when t minus 1. So that would be the cost if you did everything in one go. You'll see this in the lecture notes, but if you wanted to do everything in one go, you'll see here that your cost will grow quadratically depending on the quantity. So imagine that you decide that you do everything in one go. So this t minus 1 is 0 and t is 1. Then you do a large quantity, say 100. You're going to get 10,000 here, multiply by whatever impact you have, and this is the extra cost you're going to pay, on top of what you have paid anyway if there was no market impact. And you see it's quadratic, so it grows pretty quickly, and this, give us the sort of intuition or the sort of incentive, if you want to try to do something else, which is split the orders, because if we split the orders in smaller orders, then we should get a cost which is smaller than execution in one go. Okay. So well, we have moved just one step. Why did we compute the cost here? Is because we can go and substitute it into the Bellman equation, and then we need to move one step backwards. So in general, again, we're not going to have one step. So capital T is not going to be 1. Capital T is whatever some number we decide, so we decide maybe it could be 10, 20, depending on how long we want to execute or other market condition. So now we need to go one step backward. So what we'll do is just rewrite the Bellman equation, taking one step backward. Now we need to choose delta Vt minus 2, which shows delta Vt minus 1 in some sense earlier. And we can use a few facts from the definition. So the first fact is xt minus 1 is equal to xt minus 2 minus the quantity executed. So say, if you had 10 execution, and this is, xt minus 1, at the 9th execution will be whatever you had done earlier minus the quantity you execute at time 8. So we can use this thing to simplify our expression. So let's go step by step. This is very basic algebra. I'll go quickly, but you can, it's sort of primary school type of algebra, so it's very, very easy. But you see the result is quite interesting. So the first term doesn't change. Then we use this, we go back and substitute, this expression here in the cost. And then we make use of the fact that, xt minus 1 is actually xt minus 2 minus the quantity executed at t minus 2, capital T minus 2, of course. We substitute it here, and we get this expression for the cost. So we're trying to get rid of everything which has a t minus 1 in it. So we got rid of the xt minus 1 quantity. We want also to appear this dvt minus 2, capital T minus 2, because that's what we are solving for. So first, very simple substitution. So then, things simplify. This term, this term goes away with this term, so we have a slightly simpler expression. There is still one t minus 1 term that we want to get rid of, which is the price at t minus 1. Of course, at time t minus 2, so here we are conditioning on whatever information we have at t minus 2. We don't know what st minus 1 is, but we have the sort of dynamics for this in a stochastic form, which we've seen earlier. So we saw that st minus 1 is equal to st minus 2 plus, the impact we have in, this is cents, dollars, euros, whatever currency you like, and this is again the random component. We don't know this at, t time minus 2. We don't know what this is going to be, because there is there's a difference between the Brownian motion at t minus 1 and t minus 2, but you see it's not a problem because he enters the expectation. So the Brownian component will be set to 0 because of that. Okay. So if we go and substitute st minus 1 into the previous expression, and we simplify things a little bit, you'll quickly see that the cost xt minus 2 depends only on, at time capital T minus 2 depends only on xt minus 2 and st minus 2. So we eliminated everything which was t minus 1. You don't see the expectation anymore because we canceled out the Brownian motion, and then everything else is sort of deterministic here. One assumption actually that I made implicitly, I should have highlighted earlier, but this process dvt 1, dvt2, so on and so forth, and consequently the process xt0, 1, 2, and so on and so forth, it's a deterministic process. So it turns out that in the formulation here, you solve the problem in advance, and it doesn't really matter on the exact path that st is going to be taking. So xt, it's a deterministic policy, as they say. So you solve it once, and you don't have to solve it again, as long as the sort of the market impact stays the way it is. And this is due to the fact that we're using really an arithmetic Brownian motion. If we were using a geometric Brownian motion, things would be slightly different, but in practice it wouldn't make much of a difference. So if you don't know what, again, geometric and arithmetic Brownian motion are, don't worry. I mean, the main difference is that you see that the volatility here, the dollar or the currency volatility, it's constant because it depends on the value at the beginning of the execution, which we assume we know what it is. It's not rescaled by the value of s over time. If here we had, capital T minus 2, then things will be slightly different because the volatility will change over time. So this will have, turns out, will have an impact on the strategy, will make the solution much more difficult, but the optimal strategy will be pretty much identical. So, so that's why we sort of simplify the expression here to a model which is actually, pretty accurate if you want, or at least the accuracy that you will gain by having a geometric Brownian motion wouldn't change. So, long story short, we don't need an expectation because the process x, if you want, or our control x or our control dv are deterministic, so the expectation go away. Okay. Now, how do we go about finding an optimal solution is the usual thing. Now, the only thing we don't know here is dvt minus 2. So we have an expression, it's a quadratic expression, so we can use the usual approach of taking the derivative and of this expression after the mean, and the derivative with respect to dvt minus 2, our control, at that point in time, and then set it to 0. That's what you get here, and the solution is that the optimal amount to execute that delta vt minus 2 is simply whatever was left at time t minus 2 divided by 2. So we have 2 periods to go, so all we do is we look whatever we have left to execute, we divide it in 2, we do equal executions. You will see that also the previous execution at time t, well, subsequent execution time t minus 1, which we say we had no choice. Let me find it. Yes, it's here. You can see there is 1 period to go, and so this is xt divided by 1. So it's consistent, looks the same. Now, so we started from the very end, we put 1 step backward. So this is what we need to do optimally. We don't know, well, at time 0, we don't know yet what xt minus 2 will be, because we haven't calculated, not because it's stochastic. So let's go backward 1 more step. In order to do that, and we need these, the cost at time t minus 2, the expected cost at t minus 2, the optimal cost. So far we've been acting optimally, and then we can go backward 1 step. Let me go back to the Bellman equation again. This is the optimal cost. We started from the end, we need to go backward. As we say here, the Bellman principle optimality is you do a 1 step optimal decision, and then assume you can continue optimally. But to do that, really, as I was mentioning, the way to do it is you go backward in time. So you do something optimal, the last step, go backward 1 step, find something optimal, knowing that you did time t minus 2, you know that you did something optimal time t minus 1, then you have the optimal things to do at time t minus 2, and then you go back to t minus 3. Now, we could continue with this calculation, but they're very tedious, and it's very sort of, the concept is very simple. So I'm not going to expect you to go, it's probably a nice exercise to do 1 more step, but it's just pure algebra, basic algebra. So it turns out that at time t minus 3, the optimal thing to do is look up how much you had left to execute, divide it in 3, and go backwards. So if you do it for all time steps, if you are I steps before the end, all you do is, again, you divide whatever is left to do by the number of times that you need to go, and this is valid for all I from 1 to t, and in fact it's valid also from time 0. So if we go, here actually to be, so I in reality actually I will stop at we go from 1, so t minus 1 to capital T. So if we plug in capital T into high here, we get dv0, and what we have is x0 divided by t. Now, being discrete time, you can sort of confuse time with number of executions. Here we have t execution. This is a sort of, if you want think of it as a number of execution, but since we are multiplying by a fixed delta t interval, this corresponds to a calendar time anyway. But in this case, just to simplify a little bit the notation, think of it as number of execution you will do. So maybe you'll do 10 execution, in each one is like every minute, so 10 is capital T is 10. It's going to last for 10 minutes in this case. Execution, if execution was every hour, it was going to last 10 hours. But you divide by the number of execution you will do. So very simple. If you're the first execution, if you have to execute 100, x0 is 100. You have 10 time intervals, 10 minutes, each one 1 minute. Then you do 10 units 10 units of stock, 10 units of future contract, whatever, at time 0. So that's your very first decision. Now, what do you do at time 1? Then let's walk forward. So we have the initial condition here, and we know that all other execution are going to be the amount left at that time divided by the time interval to go. So if we go to time 1, we have x0 is what we had at the beginning. That's what we execute at time 0, and then at time 1 we're going to have t minus 1 times to go. That's the optimal thing to do at time 0. Rewrite things, and then at time 1, the optimal thing to execute is whatever you execute at time 0 as well. So if you go forward, it's always going to be the same. So all we do is we take the initial order, we divide it by the number of intervals we need to execute. We have to decide to execute, and we do a constant policy. So constant policy meaning for all the i's, delta vt is the same, and it's just take the initial quantity divided by t. So this looks like a trivial result, although it's not necessarily obvious when you formulate the problem at the beginning. And that's actually a very common strategy in the market. It's called TWAP, time weighted average price. So you basically have this constant fractioning of your initial order. You do it over time. Variation of these are the VWAP, where you end up weighting based on the sort of average quantity which is executed in the market, say historically, by all market participants. So there are certain periods of the day, for example, at the beginning and the end, where there is more volumes in certain markets. So you're not going to do it constant in time, but you're gonna adjust by the volumes. Turns out that you can, it's actually very similar once you change your calendar time into sort of activity time or volume time. So they end up giving the same results. And that's why sometimes in the paper, VWAP and TWAP, various papers, they're sort of almost used interchangeably. But here we're looking at a very simple case where, we look at things in calendar time, and we slice the order, of course, in equal quantities. Of course, this is a very specific modeling. I mean, we made a couple of very big assumptions. One is that the market has an impact which is permanent of this type, so it has a linear impact. You see, it's linear in the amount you execute. We chose a specific sort of randomness. We didn't add any drift to it, so the market has no drift. Is the random it's a drifting induced by our execution, but there is no drift, no trend in the overall market. And also what we care is really what happens on average. So we can, assuming that we are not doing few number of execution, so that this estimate is extremely volatile. We are assuming that we are doing a lot of those executions, so the variance doesn't matter. So this would be the case where you repeat the execution, it lasts for, say, a minute. You do it all day long, every day on this asset, because you have a lot of clients coming and asking you to execute these quantities. So you really can use the power of averaging and not care too much about the variance of your execution. There are more rich framework that we're going to be looking at in the future, where we're going to change the dynamics of the underlying, we're going to change the type of impact, and we're going to be changing also our objective. But the three things we assume is what's our objective, minimizing the expected cost, what's the dynamic of the underlying, basically it's a Brownian motion plus some linear impact, and we define the impact to be sort of permanent. Okay, now the next thing we need to do is calculate the cost of this strategy. So we did calculate the conditional cost time in the future, but if you're sitting at time 0, we know that this is the price, we know that this is the quantity we want to execute. What's our expected cost of the execution. Before I go there, we say one other thing I forgot to mention is that x0 divided by t. You see, it is deterministic. So we know what x0 is. We choose how much we want to execute. We choose the number of time intervals. So once we have done this calculation in this model, we don't have to do it again. Because it does not depend on the evolution of ST over time, the price of the underlying asset we are trying to execute. It is just deterministic. So this, if you want, ex post justifies also why we could take away the expectation in some previous expression here, for example. Yeah, we took away the expectation. Now, we go forward to okay, so we need to calculate this price. So if you remember the definition of the expected cost, we take the expectation at time 0. This was dvt, dvt, yes, little t, multiplied by the amount we execute. We went and substitute back the optimal amount dv for every capital T, every little t, which is x0 divided t, and you see we can interchange the expectation with the summation because expectations are linear, and that's what we get. Okay, so let's look at what's the expected price at time t minus 1, given that we are sitting at time 0. So if there was no impact and we had the sort of random walk model, if theta is 0, for example, the coefficient of impact, market impact, then this will be simply equal to S0. So prices will be so-called martingales, or here the best expectation of your price at time 0 will be what it is at the moment. One actual note on this expectation: we are not in the risk neutral measure. You'll see what the risk neutral measure is, but this is actual physical measure. This is what happens in the real world. So if there is a drift, for example, we will have to estimate this drift using historical data, observed data. We cannot use some martingale change of measure argument to solve the problem. But if you haven't done that yet, don't worry, it's not too important. So we're sitting at time 0. We want to know on average in expectation what would be the price time ST plus 1, condition on us executing this optimal policy, which is executing this amount x0 divided by t at any time interval. So here we can use the Tower property of expectation. So we forward ourselves at time little t, a generic little t in the future, and we write st plus 1 as a function of st. So it's st, this is the usual expression we were defined earlier, plus the impact plus the Brownian motion component. Now, the Brownian motion component disappears. We can substitute the optimal policy into dv little t, which is this, x0 divided by t. So we are left with the expectation of the price at time t plus the impact of that child order execution at time little t. So expectation at t plus 1 will be the expectation at the previous time plus the impact that optimal execution has at time little t. Now, to solve things, we can solve this thing recursively again. So we'll define mt. So this is a deterministic function of t, and mt is actually a specific number because it's it's an expectation. So we want to solve for this. We can solve it recursively. So we'll just rewrite what we wrote before using this definition. And the first term of the recursion is, if you look at it, is the expectation of time 0 of what the price is going to be at time 1, which is whatever the price was at time 0 plus the first impact. And in general, at time t, if you unroll the previous expression, everything it's linear. So so the expected price as of time 0. So we're sitting at time 0 and we're forming expectation for the future. So we're asking ourselves at time 0 what price we expect on average to see at time t, given there is no drift. So we we have S0, which was the initial price, plus T times the impact of one execution, given that they're all the same. That's why things get linear. So if you go back, now we can substitute this expression for MT, because that's what we had. So it's this, we can, the XT, X0 divided by capital T, we can put it on this side of the summation, before the summation, and then we substitute the value we found for MT plus 1. Okay, so basically that's the expression we get. We substitute again MT. Yes. So another thing I did is I changed the index from T from 0 to T minus 1. I change it from 1 to T in the next summation, and then I can use MT here. Just little change to simplify notation. We substitute the value we found before. Then the first bit is we're just summing T times S0, so we have T S0. The second bit, we have a summation from 1 to T of little t times a constant. This is going to be capital T times capital T plus 1. The capital T and capital T go away here. So what you'll see is you're left with this expression. Easy. I mean, I recommend you do the intermediate step, but it's trivial. And then if we simplify things, we get the result. So the result here is that the expected cost at time 0 is the cost we would have paid in any case. The cost we would have paid in any case if there was no market impact as 0 times x0, plus an extra component which is driven by market impact. So if market impact is 0, the second bit is 0, but we have two things really. It's an amount, a quadratic amount, which depends on the amount we want to execute, which get reduced by the more execution we do, the smaller is going to be the impact. Now, one thing that we need to be careful with is that this theta implicitly may depend on the number of execution you do. So if you do 10 execution a day, you're probably going to have a different impact than if you do 10 execution in 10 milliseconds. So yeah, we will go a bit deeper into that. But for now, let's assume that we sort of fix some sort of time, and we do this such that the theta sort of doesn't change too much, and we'll see that the more execution we do, the lower the impact will be. But even if we did an infinite number of execution, the impact will not go to 0. So the permanent impact will be still there. Okay, so think of having more execution, and sorry about the notation, it's a bit sloppy, but it's equivalent to say, well, we fix a time, say, 1 hour, and then we increase the number of time intervals. So we reduce delta t, and we go. Our interval between execution becomes more and smaller. This is going to be interesting when we move to continuous time. We can see that, we can take a limit for t go to infinity. So really your delta t go to 0 for a fixed time horizon in calendar time. So we do an infinite number of execution over a fixed period of time. We'll see that the permanent impact will converge to this second component. So the price you paid anyway, plus some quadratic amount that you will have to pay. Okay, so we're saying two components, cost in absolute market impact and the cost due to market impact. That's a comment we gave earlier. So as t increases, the impact decreases, but we cannot get to 0. So some cost is unavoidable. So we're going to stop here. In the next video, we're going to talk about temperate impact. So we'll change the impact model, but we'll keep the sort of objective function the same, and also the Brownian motion the same.